Sevens, happy Friday. Hope you guys have been having a great week. I know I've been enjoying some of the nice weather. I decided to work outside one day and I already got a sunburn, and it's only May. It's going to be a long summer. But I hope you guys have been able to enjoy hopefully some nice weather or being able to make the most of it right now. Today is our last day of this current unit. Today what we're going to end up doing is I looked at the responses I got for finding missing angles of triangles, like similar to questions like these. Some of you did really well. Others, I think we needed a little bit more practice. So today you're actually going to have a few more questions based off of this. I'm going to go into more detail with them. So we're going to do these practice questions. So you should be able to have a really nice review. And it's only going to be a few questions based off of that. And then we're also going to do a little bit on similar shapes, which is really easy, to be honest. I don't think it should be too much trouble for most of you. And yeah, we're going to go on from there. So to find an exterior angle of a shape. So we talked about how in polygons, if we had, let's say, a triangle like this, an equilateral triangle. So that's how we know it's equilateral. Those little dashes mean that all the sides are the same length. If I'm trying to find this exterior angle, let's take this one right here. How can I do so? Well, I have to find out what the sum of the interior angles are. For a triangle, I automatically know it's 180 degrees. If it is an equilateral triangle, all the angles will be exactly the same. So I know that the sum is 180 degrees. Therefore, I have three angles in the triangle, right? If I take 180 divided by 3, that will give me these interior angles right here. 1, 2, and 3. 180 divided by 3 gives me 60 degrees. So I know all those little interior angles, those three angles, all are 60 degrees. However, I need to find the exterior angle. Well, what happens is when I have a shape like this and I extend the line like this, this creates a supplementary angle. As you guys remember earlier in the unit, supplementary angles they look like this. We have a straight line and an angle comes out of them. And we need to find out if we are given this angle, let's say it's 67, we need to figure out what this angle is. How can we find that out? We know that supplementary angles, that straight line, always adds up to 180. Okay? So 180 degrees, that means if this is 60 degrees right here, 60 degrees plus this must add up to 180. So if I take 180 minus 60 degrees for that interior angle, therefore the exterior angle is 120 degrees. Okay? So you guys did really well with the regular polygons where you had to figure out what the full sum of the angles was inside of there, and then you figure out what the each individual angle is and to find the supplement. Most of you did really well on it. I was really impressed, so I'm really proud of you guys. The only one I think that we might need to do a little bit more practice on is if you have a missing angle of a triangle, finding that supplement. So this is very similar to finding the one to regular polygons. However, in my opinion, I think it's a little bit easier. Who remembers what number all the interior angles of a triangle must add up to? They must add up to 180. So all three angles of a triangle, regardless of the triangle, must add up to 180 degrees. So Remember when we had worksheets and we were doing questions way back when we were finding the missing angle of the triangle? So let's say I was trying to find this angle right here. How do I find it? I take 180 minus 37 minus 63. So 180 minus 37 minus 63. This gives me 80 degrees. So this angle right here is 80 degrees. However, I need to find whatever B is. I need to find that B angle. How can I find that B angle? Well, I have a straight line here. I know a straight line, even if it's cut somewhere in the middle, must add up to 180 degrees. So if I have a straight line right here and 80 degrees, this here, whatever B is, must add up. This B plus 80 must add up to 180. What would it be? It would be 100 degrees. So therefore, B is equal to 100 degrees because 100 plus 80 equals 180. Let's try this triangle right here. First of all, in order to find out what D is, this angle D, I need to figure out what this angle right here is. How can I do that? Well, I take my 180 for my interior angles of the triangle. So I'm talking about 1, 2, 3. I know that this little square here means it's 90 degrees. It always, always, always means 90 degrees. So I do 180 minus 90 and then minus 46. That gives me 44. So therefore, this angle right here is 44 degrees. How can I find what D is? Well, 44 degrees, this is a straight line, plus D must equal, 44 plus D must equal 180, because a straight line is 180 degrees. So what can I do? I take 180 minus 44, that gives me 136. So therefore, D is equal to 136 degrees. And there you are. So you're going to have a couple more questions today based off of that, not too many. It shouldn't be anything too bad. And we're going to go on to our similar shapes. So, similar shapes. Here's a question for you. If a triangle is enlarged 2 times its original size, is it similar? And what I mean by similar is, obviously, if I made this triangle 2 times bigger, as in, let's say I took a ruler to my screen right now, and I measured out this side right here, and just by putting a ruler up to my computer screen, I can see that it is 8 centimeters, for example. And I measure this side right here, and I find out it is 6 centimeters. And I measure this side right here, and I find out it is 10 centimeters. All right, but now let's say I enlarge my screen 2 times. 1, 2. Obviously, these are no longer the same lengths. That's clear because there's no way that this is 8 centimeters anymore. This is much bigger. However, if I enlarge a triangle that much bigger, do these angle measures remain the same? As in, if it is if we say this is 90 degrees, but then I enlarge it 2 times, so 1, 2, is it still 90 degrees? Yeah, it is. Despite the lengths of the triangle, or the triangle being bigger and the measure being bigger, these angles always stay the same. If this was 47 degrees originally, it's still 47 degrees. However, our lengths change. What if we are given a triangle that doesn't have angles in it though? I can clearly tell a triangle is similar if I'm given the angles. Because if I have a triangle, This is, let's say it's an equilateral triangle and they're all 60 degrees. And then I have a bigger triangle and these are also all 60 degrees. Obviously, these are not perfect equilateral triangles because I can't draw very well. But I can clearly tell, oh yeah, that's similar, no problem. I don't even have to really think about it. But what if I'm not given the angles? What if I'm only given side measures? So let's try this out. I'm going to draw two triangles that are only giving you the 3 side lengths. It's not going to give us any angles. We have to determine whether or not it is a similar shape. So here's one triangle. And here is another. Now, just by looks, oh, sure, they look similar, but the only way I can tell for sure is by looking at the side lengths. 12, 6, 10, 12, and I have to determine whether or not these are similar just by using these side lengths. There's 2 ways I can find out if they're similar. You need to try both ways. If they both don't work, it is not a similar triangle. If one of them works but the other one doesn't, then it is similar. If they both work, then it is similar. The first way is by doing simple addition. These side angles here are meant to be similar. So this is a triangle that wasn't turned or anything like that. It's just bigger. What's the difference between 6 and 8? I added 2. What's the similarity between 12 and 14? I added 2 to 14, or I added 2 to 12. 10 and 12? I added 2 to 10 to get to 12. So that's one way, is just by doing simple addition. Do all the triangles do they all increase by the same amount? So in this case, all 3 sides increase by 2. So if this was centimeters, if these were all in centimeter measures, they all increased by 2 centimeters. So this got 2 centimeters bigger, this got 2 centimeters bigger, and this got 2 centimeters bigger. That's one way I can tell. They all add up by the same amount. So they all increased by 2. That's one way to figure it out. We have this triangle right here. Oop. This one is 3. Let's just say for the sake of argument, these are all measured in centimeters. Just to make things easier, rather than changing units all the time. 3, 10, and 9, and this one is 30, 9, and 27. How can I figure out if these are proportional, as in this is a similar triangle? Well, I can try my addition trick. From 3 to 9, oh, that increased by 6, so plus 6. 10 to 30, oh, that increased by 20. And 9 to 27, oh, that increased by 18. Huh. But does that mean they're not similar? No, not necessarily. Because I can find a relationship between all these numbers. So, who remembers fractions? I take these numbers here. So let's say 3 and 9. Because these are the same sides of a triangle. It's just a bigger triangle. What I do is I put 3 over 9. 9 would be my whole number, 3 would be my part. Next one is 10 and 30. Those are meant to be the same. So I put 10 over 30. And then now I have 9 and 27. So I put 9 and over 27. Why did I do this? Because who remembers finding the simplest form of a fraction, where you divide the fractions up to make them into the lowest common term, or the lowest fraction. 3 over 9, 3 and 9, they both fit into 3. I can divide both numbers by 3. So I can make this fraction, I'm just going to draw it over here because I'm running out of room. 3 divided by 3 is 1. 9 divided by 3 is 3. So 3 is 1/3 of the size of 9. So that means if these were drawn properly, that means this length right here is 1/3 of the length of 9. 10 and 3. Here's the thing, whenever you have numbers that are divisible by 10, you don't even have to divide it. What am I left with? 1 over 3. All right, last one. I can divide 9 by 9, and I can actually divide 27 by 9 as well. So I know, because I know my times tables, that 27 can be divided by 9. 9 divided by 9 is 1. 27 divided by 9 is 3. Oh, would you look at that? 1/3, 1/3, and 1/3. Huh. That means this triangle here, all the side lengths of these triangles are 1/3 of their enlarged counterparts. Therefore, they are similar triangles. Another way you can look at it is if you know your times tables, 10 times 3, 9 times 3, 9 times 27. Or sorry, 9 times 3 equals 27. That's another way. The reason I show you the fraction way is because I'm going to show you one more shape. I'm going to show you one more way that these shapes can end up being similar, and this is why I showed you the fraction way, is because I have these two triangles right here, 1 and 2, and we have 15, 18, 9, we have 6, we have 10, and we have 12. Right off the bat, let's try adding. 6 to get to 9 is plus 3. Okay. 10 to get to 15 is plus 5. And 12 to get to 18 is plus 6. Huh. Okay. Let's try multiplication. Can I multiply 6 by something to get to 9? Not a whole number, that's for sure. Can I multiply 10 by something to get to 15? Nope. 12 by something to get to 18? Nope. So this is why I showed you the fraction method. I take my similar sides, so 6 and 9, 10 and 15, and 12 and 18. 12 over 18. I need to find the simplest form. I can divide 6 by, well, they both can't go into 2, but I know that both 6 and 9 can divide by 3. 6 divided by 3 equals 2. 9 divided by 3 equals 3, so that's 2/3. Okay. 10, I can't divide both by 2. Well, can't divide both by 3. Huh. However, I can divide both by 5. Ten divided by 5 is 2. 15 divided by 5 is 3. 2/3. 12 over 18. Well, I can divide both by 2 to start out. 12 divided by 2 is 6. 18 divided by 2 is 9. Oh, look at that. I faced this before. So I just divide both by 3. This equals, I'm just going to put it up here, 2/3. See? So therefore, I can say that all these side lengths right here on this triangle are 2/3 of the measure of the enlarged version. And that's why I showed you the fraction method. Keep in mind, when you're looking at similar triangles, I've put them on the screen that they're not turned or anything, that they were literally just made bigger. However, sometimes you have triangles that, let's say, one's like this, and then one looks like this. Keep in mind that sometimes the triangles are turned around. You have to find the side that corresponds, as in the side that matches up to the enlarged version. So we have to find the same sides. Well, the long sides are pretty easy to identify. Those are our long sides of those triangles. We have our shorter sides, so this one here and then this one here. They're both the shortest sides of those two triangles, and then these ones here are both the medium ones. And that's how you can kind of figure that one out. So you have to pay attention to make sure that when the triangle, that just means either you redraw the triangle so they're both turned around in the same direction, like I was showing you with my previous examples, or you're able to just kind of look at the triangles and match up which sides kind of pair up together. So far I've only showed you similar triangles. Let's try one more. Let's not do a right triangle anymore. Let's do something different actually. I say not to do a right triangle, and what do I draw? A right triangle. There we go. It's a little bit better. All right, those are my triangles. Let's give them some numbers. I have, let's say this long side here is 8. This side right here, let's say is 7. And this one right here, let's say is 6. Or actually, let's make this a little bit different. Let's make this 5. All right, this triangle right here, let's say this one here is 15. This one here is 10. This one here is 7. Well, first of all, I can try adding. Which sides are similar? Actually, I'm going to redraw this triangle because I don't want to show you ones that are tilted the same direction. Sorry about this. So I had 8, 9, and 6. Okay. Now let's do that. First of all, let's find a missing side that we can easily tell. Oh, these are both the longest sides of the triangle. Let's do that one. So I have 8 and 15. What plus 8 equals 15 plus 7? Okay, that's fine. Let's try the shortest sides. Oh, 7 is the shortest side and 5 is the shortest side. What plus 5 gets to 7? 2. Okay, right off the bat, I can tell you that's not going to work because one is 7 and one is 2. So adding's not going to work. So let's try my fraction method. Longest side here is 8. I'm going to put it over 15. My shortest side here is 5, and my shortest side here is 7, so I'm going to put 5 over 7. And my last one here is 6, and this one here is 10, so I'm going to put 6 over 10. Now I need to reduce these fractions as small as I can. 8 and 15. Can I make this fraction smaller? No, they both can't go into 2. Both can't go into 3. Can't go into 5. And that's it. Can't make them any smaller. So that's it. 5 and 7. Can I make those any smaller? Nope. 6 and 10. I can make that smaller. So I can divide both of these by 2. Now I have 3 over 5. That's as small as it's going to go. Are these fractions the same when they are reduced? Nope. So these two triangles are not similar. All right. So today we discussed the two methods to find out if you have a similar triangle, either by adding, all three sides are added by the same amount, like our first example, they all were +2. They could be +5, they could be +7, but they all add up or they all increase by the same number. The other way is by just making them over fractions. So finding the sharing side is like, let's say, like I showed you with the longest side of the triangle. Oh, the longest side with the bigger triangle, I put the other longest side, I make them into a fraction. So for example, I gave you 8 and 15. They're both the longest sides of these triangles. I put it into a fraction. Make sure it's a proper fraction where the top number is smaller than the bottom number. Makes life much easier, trust me. Then I try to reduce those fractions into their simplest forms. If they all reduce into the same fraction or into similar fractions, as in like they all reduce into 2/3 with our one example, then we know it's similar. All right, so that's it for today. You are going to have a couple more questions based off of finding the missing angles like we did here. And then you're going to have a sheet that basically just tells you, are these two triangles similar or not similar? And that's it. You just label if they're similar or not similar. And that's it. Otherwise, I hope you guys have a fantastic weekend. Be sure to email me if you have any questions. Thanks for the amazing work you've been doing. I'm honestly so taken aback by all of you. Like, you've all been working so hard. You've been doing amazing. Like, I emailed you out all your grades for this current unit, and I was really thrown away. Like, you guys are really rocking it, and I'm so incredibly proud of you. Like, this is a very, very tough time. Not everyone, it's tough for everyone, but you guys are really rising to this challenge, and I'm incredibly, incredibly proud of you. Thank you all so much. I hope you have a fantastic weekend. Enjoy some of the nice weather, and I will see you guys on Monday.